All right, let's work on this problem where we have a distributed load and we are asked to find the maximum intensity of the distributed load indicated by the W, so failure doesn't occur. We are given a couple of different problems actually that the max load on FA or on A, my bad, and max load on B. So we're given this, but I'm not going to talk about the numbers right now because they can be different numbers or anything. But in a situation like this, where they give you a max load on both of these, you have to actually calculate them out with respect to the distributed load because either one of them could be the failure. You can't just simply put that number in as one of those because you don't know necessarily the way it might be distributed. If it's more heavily weighted on A, more heavily weighted on B, you can't just simply put that max load in either of those. So first thing we're going to do is draw our free body diagram. So we have our bar or member. We're isolating it by itself. Terrible drawing, my apologies. We're going to put in our loads. So we have a pin connection at B, so we have BY and BX. And then this force, because it's a pin or a simple support or a roller, it will be perpendicular to A. So we need to actually indicate it just perpendicular to A and give it its angle because we know its angle. This is 30 degrees and we know that this is then 60 degrees. It is not appropriate to draw in this value that you see here, NA, as well as AX and AY, because those are components of it. So just draw one or the other, but in this case, you really want to draw just NA at the angle that you know, so you have only one unknown. We also have our W, which we're going to draw as its resultant, and the resultant of that will be 4W. It's the area under the shape that it's given. And it's a simple rectangle, so it's the base of 4 times the height of W. It is not appropriate in this case to show the free body, show it as just W, because then it's not a force, it's a distributed load. And in our free body diagrams, we show forces. We also want to include then our dimensions. This is 4 meters. This distance is 3 cosine of 30 because this distance is 3. So we know this x component is 3 cosine of 30, and we know that the y component is 3 sine of 30. We need that distance as well. So that is all, and then I have my coordinate system, x and y. So that's all I need on my free body diagram. Now we can do our equations of equilibrium from this. We should also have the assumption that the weight is negligible. All right, so in the x direction, we have some of the forces in the x are equal to, oops, this is x, negative bx plus NA. The x component of NA is going to be NA cosine of 60 degrees is equal to 0. Then we have the sum of the forces in the y direction are equal to By minus 4W plus NA sine of 60 degrees. The y component of NA is equal to 0. Then I will sum my moments about B, so I get rid of those two unknowns. I have 4W times its moment arm, which will be halfway, 2 meters, minus, that's positive because it's in the counterclockwise rotation, but the x component of NA, NA cosine of 60, will be in the clockwise rotation, so it's negative, and its moment arm I was starting with the y component. So the y component, sine of 60, is moment arm is this distance here, 3 sine of 30 degrees. And then I have my x component, NA, no, I was right the first time. This should be the x component. So this component here, the x component, has a moment arm of this, and then my y component, NA sine of 30, has a moment arm of this plus this, 4 plus 3 cosine of 30 degrees is equal to 0. So now what I'm going to do is I'm going to solve these with respect to W, because what I'm trying to figure out is this W. So this equation here has only two unknowns, NA and W. So I'm going to solve NA is equal to 1.2376 W. So I still can't really figure this out yet. I'm not going to stick that A value, the max load, in here because I don't know if it's going to be the max load at A or B. I can't do that. So I am going to just leave it like this, but then I can put that into this equation and get that, and I can get By with relation to W as well. So By is 2.9282W. So I'm able to find By that way, and then I can put Na also into the x, and I can get Bx is equal to 0.6188W. So I have these three, and I'm given a max load on A and a max load on B. So in order to actually get this with relation to the max load on B, these are just the x and y components of B, so I need to find the magnitude. So the magnitude at B is going to be the square root of bx squared plus by squared. So I'm going to square this one, and take the square root, and get the value for B with relation to W is 2.9282W. So now I have these two that I can test and see our W. So I'm going to rewrite those. I have NA is equal to 1.2376W, and B is equal to 2.9282W. If I'm given that a max load of A is equal to, or has to be, sorry, A has to be less than 5 kilonewtons, and B has to be less than 10 kilonewtons, I put those into these equations. So I get 5 kilonewtons equals 1.2376 W, and I can find the max distributed load for this case is 4.04 kilonewtons, and then I can put 10 kilonewtons in on this side for B equals 2.9282 W, and I can solve for W as 3.341 kilonewtons. This one will be our limiting factor, so that's our max distributed load for this case. In the case where we have a max load of NA has to be, or A, sorry, has to be less than 8 kilonewtons, and B has to be less than 4 kilonewtons, we do the same thing. 8 kilonewtons equals 1.2376 W. W needs to be less than 6.464 kilonewtons, and over here 4 kilonewtons less than or equal to, doesn't really matter right now, 2.982 W, and then W has to be less than 1.336 kilonewtons. Again, that's our limiting factor in this case.